All right, time to dive in. We're going to deal with range and continuity in this particular section of notes. Hopefully I'll break it up into smaller chunks that you can digest a little quicker. But the three functions that are not on your particular notes, they're filled in here. So take a second, pause, write these in, and then now we're going to talk about range, as you'll see above, I did in purple, is the set of all y values that correspond to the domain of the function. So we're dealing with vertically all possible output or y values. And the first example there, this graph is actually like 1 over x, but the 2 on top actually makes it a little bit more slender, a little taller. But the range, you'll notice, vertically speaking, there's a gap at 0. And so we'd write that negative infinity to 0 with the union break 0 to infinity. The radical in part B, now the domain would go negative 8 to infinity, but the range vertically starts at 0 and goes on up to infinity, and it includes 0. Then the last one, that x squared, is a parabola down 4, so when we think of range, the lowest, negative 4, is included, and then you go on up to infinity. So again, this is vertical. Range is up and down. Then continuity in general, if you're wondering what the word means, relates to how continuous a function is. So, and there are breaks in continuity that you're seeing below in these graphs. So graphically speaking, a function is continuous if there's no break or place where the graph comes apart. So the example of that is this first one here. That's definitely a continuous function. Then the rest have a break. Here's a removable discontinuity called a misplaced point. Removable discontinuity means you can fill the discontinuity and make it continuous. I should say it's kind of it's a funny way to look at it. But my favorite way to call this one is misplaced point, and but it's defined as a removable discontinuity. So is a hole, the one that's next to it. One of them has a replacement value to fill that discontinuity, f of a. The other one doesn't, but I usually call it misplaced point and hole. Notice they're discontinuities, they're breaks in the graph. Nothing to be too upset about or too tedious about. Asymptote, the very last one, you notice there's these places where the graph doesn't touch, and that is itself an infinite discontinuity. We call them asymptotes. The jump discontinuity you see here second to last, that's pretty self-explanatory. You're seeing a leap somewhere in the graph. But what makes it interesting is if we talk domain in each case, domain, on the first one obviously, infinity, negative infinity to infinity, all real numbers. The removable discontinuity, we're seeing this actually here, that's actually negative infinity to infinity for the domain as well, because there is an output for every single x input we put in. Even here, when you put in a, you get out f of a. So that's continuous. The domain exists for all inputs of x. The whole, however, that's where you have a break at a. So you want to break up your domain into negative infinity to a. Lift your pen back down just above a onto infinity. The jump discontinuity, there's a value for all x. So when x equals a, there's an output value. So there's always an output for any given input, even though there's a gap there vertically. At the end, asymptote, negative infinity to a, you see that break, and then a onto infinity. The domain in this case is used to help describe a little bit what's going on there. Hopefully it sheds some light on here for you. That's the end of the road. For this section, we'll go on to the next chunk, and enjoy.